Good afternoon, and thank you for joining today's webinar from Spec Innovations, How to Perform 21st Century Systems Engineering. My name is Elizabeth Steiner, and I will be the moderator for today's webinar. First, I would like to make an announcement and go over some housekeeping before we get started. Due to COVID-19, we understand that many of you are now working from home. This can make it a challenge if you have been using Innoslate Enterprise at work. For our current Innoslate Enterprise customers in the US, we're offering a special 30-day Innoslate Enterprise license, so you can work from home. An announcement will be going out soon. Please contact us at sales@innoslate.com to request this 30-day license. During the presentation, feel free to send us questions and we will get them answered in the question and answer part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through Twitter using the handle @Innoslate. The webinar is being recorded and we will make it available to you after the live presentation, so be sure to keep an eye out in your inbox. Slides are available in the handout section of the GoToMeetings panel. Now I would like to introduce you to our presenter, Dr. Stephen Dam. He'll be discussing his new book, Real MBSE, Model-Based Systems Engineering Using the Lifecycle Modeling Language and Innoslate. Dr. Dam is the president and founder of Spec Innovations. He's been involved with research, experiments, operations analysis, software development, systems engineering, and training for more than 40 years. Dr. Dam participated in the development of C4ISR Architecture Framework and DoD Architecture Framework. He has also received an Expert Systems Engineering Professional Certification from INCOSE. He currently is applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send Dr. Dam any questions through the LinkedIn Innoslate users group or send him an email if you have any questions after the webinar. And now I'll hand over controls to Dr. Dam and we will get started.
Thanks, Elizabeth. By the way, we did do a version of this for INCOSE recently, but I wanted to talk a little bit more. These are always a little difficult because you're really not supposed to be doing a lot of selling. So this webinar, we'll probably do a little bit more of that, but not so much. I mean, the real focus we have and what we've had in developing our Innoslate tool was that how we can really help make the future, possible. So what people have been envisioning. So particularly, I'm going to talk briefly about INCOSE's Future of Systems Engineering Initiative and what they're trying to do with that, and talk about one of the topics that came out of that, which is why is systems engineering today too slow? And then get back to, well, what do we need in this century for systems engineering? What should we be doing? What should we be looking for? And then what the future systems engineering that we have already presented as part of our capabilities within Innoslate. So INCOSE's FUSE initiative, if you're not familiar with it, the International Council on Systems Engineering has a variety of different projects and approaches and initiatives, working groups that they do. And so this is actually an initiative which cuts across various working groups within the INCOSE structure. And the purpose of FUSE is to try to position systems engineering to leverage the new technologies in collaboration with allied fields. So looking at what we're trying to do in that future and enhancing our ability to solve emerging challenges and, of course, promote systems engineering. That's part of what we're trying to do. And particularly that ties in with another initiative that's going on within SASC, within INCOSE, which is the Value of Systems Engineering Initiative. So there's some multiple as you are going on. The person who's to point of contact on this is Tom Shortell. So if you need to get in touch with him, if you want to do some work in this area, this is a great one. Good contact for you. This slide is about a year old, but I believe that the current updates are using very similar types of slides. So looking at some of the things that they said, well, what's good, what is good, looking good be once we deliver this, and looking at how everything has for self-learning, improving simulations for dynamic objects, architecture techniques, AI, demonstrating AI. So those kinds of things are all part of it. But the thing that hit me was what is stopping us now. Data availability and usage is always a problem. It's always difficult to keep things separate. We have mechanisms for doing that within Innoslate to help you with that problem. Also, knowledge and research is something that goes on all the time. We try to stay abreast of all the latest trends and capabilities and research work that's been done. Unfortunately, the CSER conference, which was the conference on systems engineering research, has been postponed because of the situation. So hoping we'll be able to do that later this year. And of course, assurance, trust, and understanding of the technology. So there's a lot of concern about using cloud-based technologies, particularly, has caused a lot of concerns because people think it's the public cloud and it's open and available to everybody. It's not. It's a highly secure environment by comparison to that kind of environment. So, and there are very high security versions of that that are available today. But the one that really hit me was the systems engineering is too slow to keep up with AI advances. I don't know why that should be. And so I wanted to think about what it is that's causing that problem and look into that a little bit more. So let's take that particular question and delve into it just a little bit more. So one of the things that looking at what we've done and how do we do things in systems engineering is we've applied a number of different techniques or languages all through the years. In the 60s, it was flowcharts. I still remember one of my first flowcharts, getting a little template and you draw your first flowchart, and oh, this was pretty cool. Of course, back then we were using cards, and doing a flowchart was actually something that took time and actually was a drawing thing with a paper, and then if you got it wrong, you had to go basically start a new piece of paper very often. And so it was very time consuming. So most of us would actually create our code and run the code and get it working, and then use the flowcharting technique to document it. So that's what really happened. And we still sort of do a lot of that today. About the same time in the late 60s, early 70s, a technique called SREM was being developed. And that was actually very interesting. That was work that TRW was doing for the government on a variety of projects. And that was looking at software and systems engineering together. And they had quite a bit of success with that. But since it was a government project and so a lot of the work was classified, it wasn't published and it wasn't out there as available as you might like it to be. Fast forward another decade, and data flow diagramming was kind of a big deal. That was, again, heavily influenced by software. You see your software, right? All the software kind of focus. IDEFs, same thing, basically, state machine modeling. There became an idea of computer-aided software engineering tools, CASE tools, but then we had a version that we called computer-aided systems engineering tools, which were CASE also, but you put an underscore under the SE. That's how we tried to differentiate between them. But again, most of the tools were the same. I mean, I was using Jordan DeMarco data flow diagrams and things like that from the 70s and in that time frame, because they were available now on the PCs, and so we could do things like that. About that same time, a tool called RDD100 was being developed, and I got introduced to it a little bit later in the decade, if it wasn't in the early 90s. And that was a very interesting capability. That took a lot of the technology and thought process that was developed in SREM and enabled it to be developed into a really quite a good tool. In the 90s, we had the EFFBDs and the object-oriented analysis and design. So the two were kind of competing against each other. EFFBDs was particularly embedded in Vitex's core tool. Also Cradle, I believe, used something similar kind of approach. And the object-oriented design analysis, which ultimately became different varieties, became unified modeling language, UML, again, was very focused on the software side. So you had a systems engineering kind of approach and a software engineering kind of approach. But somehow the software engineering approach seemed to dominate, and people were using it a lot. I know on a major project we were doing for the Department of Defense in the late 90s, early 2000s, we used UML on that project, and it was not overly successful, to be honest. People were quite disappointed with the capabilities. So Some people felt that what we needed to do was expand UML. So SysML was developed in the 2000s. So I think it was released in 2007, was officially put out there. But again, it's a profile on UML. So it's a UML based approach. So again, very software focused, software centric ideas and approaches to it. In the 2000s, 2010s, we were still using SysML. It's been kind of pushed as a major thing. INCOSE's gotten behind it and pushing it pretty hard. A lot of groups are jumping on board, but a lot of us were not very comfortable with it, and still are not comfortable today. And I'll give you a lot of reasons why as we go through here. But so a group of us got together and created the lifecycle modeling language. And that's an open standard that was developed by a group of us. In version 1.0, we had a general ontology and some diagram types that we had suggested. And then in version 1.1, which was so the first release of the LML 1.0, I believe was like 2012. And then 2014, we went back and said, well, how would we extend this to SysML? And so that ontology was included in here in it, and it is available in the current standard. What this kind of always gives me an idea of is systems engineering always seems to be about 10 years behind the software world. Things keep changing in the software world pretty dramatically, yet we don't always seem to keep up with that, or we're adopting techniques when they're abandoning them. I'll show you an example in a minute. So let's step back and play we're systems engineers and say, well, what do we need? What's the functional needs of today for systems engineering? Well, we need methods to capture and visualize tremendous amounts of information. You know, when I was originally started in the 80s, working 70s and 80s, working at Los Alamos, we were excited when we had a 1 megabyte machine. That was something. Well, now we're talking exabytes. So that's orders and orders of magnitude beyond what we even dreamed of back then. So that was that. So now we can get. Now we're starting to go, well, wow, how do we deal with all this information? Now, if you have a lot of that information, not only capturing and visualizing, but now you got to be able to store it, and you got to be able to retrieve it. So again, very hard things that have to be done, and it's done differently. You know, many tools will try to have you scroll through things, and you can't do that with that kind of massive amount of data. You have to have smart searching. It has to help. In fact, what the technology needs to do is help identify information that we need to see and bring it to our attention. So that's the kind of thing we're looking to do in the future. The other thing that we recognize, we needed not just the technical side of the problem, but also the programmatic. Because for systems engineers, as the recent book with INCOSE and PMI recognizes, there's an integration between those two disciplines that's really more tightly coupled. I like to think they're 80 to 90% the same discipline. It's just you're doing it for different things. The program manager is optimizing cost, schedule, and performance for the program, but the systems engineer is doing that for the system at the same time, and they have to work together to mitigate risk in both areas. And so that's also part of the working together. So that part's really critical and needs to be thought of as part of our job early on in the process. The other thing we need to do is move data around easily between applications. We got to be able to, we can't just be data locked all the time into one application and one way of doing things. Data's got to be able to be moved. It has to be able to be seen. So that ontology has to be open so people can work with it and use it. So obviously the language has to still enable decomposition and abstraction, because that's what we do in systems engineering, right? We try to break down the problem so we can understand it, but then we can oftentimes bring it back up to a higher level in a different way, and that gives us that new way of looking at the problem. And so that technique's critical to what we do. And so I feel like we need a systems engineering language, not a software engineering language. We need a language that's simple enough that systems engineering can use it easily and use it for all of the stakeholders. Now, a lot of you may be saying, well, gee, SysML does all this, right? Well, what we found was that's not the case. And interest in SysML, if you look at the Google Trends here, and this is a couple years old, but I believe it's still correct. I should have updated it for this chart, but to take a look at the Google Trends and make sure you type out unified modeling language. Don't do UML. UML means many things and these things. So you can see the interest level, and that's because if you look at what has happened in this time frame, something called Agile came into vogue in the software world, and so they're not even teaching it in a lot of the schools these days, and haven't for a while. So that's something that people have to realize, that your software developers may not even understand UML. So, and I think a number of you who are using UML have probably found that out. You hire a software engineer and all of a sudden you have to train them how to use UML, which you probably were shocked by. I know I was. And so if you look at Agile, what does it require to start with? It's functional requirements. That's what they're looking for. That's what they want from the systems engineering community. So we need to kind of get back to that whole functional analysis approach to things. And the problem with SysML and UML that we ran into on some of these large programs was we try to brief them out we show these diagrams to some of the stakeholders, and they'd look at us cross-eyed and say, what are you trying to tell us with this thing? Because they didn't understand them. They weren't clear and they weren't complete. And I must say, I find them difficult to follow and understand even. And I've certainly studied them a fair amount, and I just find it to be confusing. And so anyway, I mean, maybe I know I'm only a PhD in nuclear physics, but I can't quite figure those out. Anyway, so the systems engineering really requires communication with all stakeholders. And we're dealing, I don't know about you, but I deal with contracts people all the time, security professionals, people who are just not versed in anything to do with software. And so I have to be able to communicate with everybody. And if you have to be an expert in SysML's lexicon and diagram specification, who are we communicating with? So, and it's worse than not just being able to understand. Again, I find SysML lacking in the programmatic pieces, particularly. You have to make up, you're making your ontology up on the fly, particularly things like risks and issues, decisions, schedule, cost. There's no diagrams or entities that would force you to head down that path. I had the exact same problem with the DoD architecture framework. If you read my book on the DODAF, it has the same problem. It's not dealing with all the parameters we need to deal with. And so the lack of ontology, of course, has been noted by the SysML community. They're working hard on it. I hear there's something out there, maybe a draft of something, but probably a few years before it gets finalized and they'll have a final product. But will it still be complete enough? Will it still do all the things we need it to do? I don't think so. And that's what I'm concerned about. And so, but the fact that gee, maybe there's already a language out there that does this, why don't we just look at that? So what's needed for the 21st century? So first of all, we need a methodology. Anything we work on, we need a technique, process, and tools. We know we need that. That's fundamental to systems engineering. It's fundamental to how almost anybody does any kind of analytical work. So let's talk with my methodology. That's the one I'm familiar with. That's the one we've developed over many years because we found it works. I started our company in 1993. And the first thing I did was get a copy of Mill Standard 499B at the time. It was in draft. And I liked that process diagram they had for it. It made a lot of sense to me. It always has. And so we've used that as a basis for a lot of our development over the years of our processes. And we'll talk about that a bit more in a minute. The technique is the lifecycle modeling language. We definitely want to start from there. That's why we helped develop that technique. We think it's we found it as we've applied it over the last 8 years. It's been very valuable in helping people understand things and work with it, and easy to work with and understand and complete. It's actually, we find we don't extend it very much from domain to domain. So that makes it a very usable technique. And of course the tool, we need a model systems engineering tool, a real MBSE tool, something that does what Dr. Vanneman calls concordance. It gives us we have the data, and we have the views and the rules for the views, and that if I have an object that's been created and it belongs in one picture, it's in another picture too. Because otherwise you're doing all the configuration management yourself. So these are very fundamental things we need to do. So let's talk briefly about LML if you're not familiar with it. And if you want, there's a very inexpensive book. Dr. Vanneman and Dr. Sellers and myself wrote this book with some inputs from the rest of the committee. And you could see, if you compare the size of that book to the SysML texts that apparently are required for really understanding SysML, it's a lot simpler. And it's a lot cheaper. It's $15 so on Amazon. So fairly easy to go get and understand. Particularly since all of us teach, we all wanted to have something that the students didn't have to pay an arm and a leg for to have as a basic textbook. So LML has a simple taxonomy. We have the functional class actions, the artifact class to capture documents and be a container for statements and requirements particularly. Assets are the physical objects, and then a subclass of that's the resource, which is resource modeling is a critical item in any kind of functional analysis, as you'll see. Also characteristics, that gives us kind of floating attributes you might want to think of for assets or anything else in the ontology. Measures are where you put your metrics, easy to remember that. Connections an abstract class and has two concrete classes, which are the conduit, which is your physical pipes, and logical, which is a relationship. So again, very easy thing to understand and work with. A cost is an independent variable. We think that's critical. We want to make sure everybody understands about cost. Decisions, we're supposed to be capturing decisions. We're supposed to be understanding what the decisions are. We want to be able to use those in the future to improve the process. And so that's important to have captured. Input output is the data flow between particularly actions. And then they are transferred by conduits. So now this starts tying the physical and functional model together. So you want to think about that part of it. We thought location was important. Again, back to my physics background. If I don't deal with time and space, I'm not gonna be very happy. So I know that's important for everything we do. So having those were kind of key. And then risk, of course, as an explicit variable that we're tracking, and we can then update and link to the things that cause the risk, and what's mitigated, what the mitigation strategies are, and all those kinds of things are part of risk. Statements is the general class of textual information, so it's more meant for contextual purposes, whereas the requirements subclass is very specific. It has quality attributes. What makes a good requirement? Clear, complete, consistent, things like that. So we have those parameters as attributes of the requirement. And then time. Time, again, is another variable that's very important for scheduling purposes, particularly capturing milestones, things like that. That's what we use that for. Again, LML is a non-proprietary standard. A lot of people I hear out there are saying that LML is something only Spec Innovations has. It is available anywhere. We prototyped it originally using Core. So, it annoys me when I hear that misinformation that's out there. So that is just not true. So LML is out there, and it's available for anybody to use in any tool they want. Anything that has a schema extension capability can use that schema, basic schema. So what makes it, you say, well, gee, that's kind of simplistic. You have just those few classes of information, 20. And so is that enough? Well, what makes this very powerful is the relationships. So every class is related to each other by often even more than one relationship. And so that's actually very helpful in understanding how this works together. And of course, we also have attributes on the classes and attributes on the relationships. So if you think about it in terms of actual language, our classes of information or our entities are the nouns of our language. The relationships are our verbs. The attributes on the entities are adjectives, and our attributes on the relationships are our adverbs. So simple, easy language. It's all there for us. It gives us that richness of the language we need. The one thing you can't do in other tools perhaps is the action diagram. That's one of the unique diagrams in LML. You can do something similar to it in some of the others, but it's not exactly the same, and I'll explain the differences in a second here. That's our functional model. That's the one we use and tie into the discrete event simulators and things like that in the tool, as we'll talk about in a minute. And then the physical diagram here on the right, again, that's a physical diagram. It can be just boxes and lines, or you can make it pretty pictures and background. And any way you want to visualize the physical elements of it, we think is a good idea. And then the third one that's required is the traceability diagram. We use a spider diagram for that purpose. There are a lot of other ways you can do it. I've seen it done other ways, and it's perfectly fine. And that would be equivalent. The whole idea is traceability. I have the way to show the different entities that I have and their relationships between them. So again, that ER diagram would be perfectly fine. Entity relationship diagram would do that job fine. By the way, what makes the uniqueness of the action diagram, though, is if you notice, there are no constructs in it. There's no symbology where I've got the or is a little symbol of some kind. So it's each decision point is actually a special subclass of action. And that's important because now that action is allocatable to who or what makes that decision. Okay, so that's a way we can build in things like command and control structures within the processes, or information assurance activities for making security decisions as you're going through the process. So you can see that's the one thing that is very unique about this particular language. So processes. We have, again, a number of processes. If you notice the one coming down on the left, it looks a lot like MIL Standard 499B. Gee, I wonder why, because it is. It's the same process. Coming up the V is a little bit different one we came up with to try to show what do you do in the V and V stages of things. And so again, our 499B process is a little different than what their intent was. The circular part of that one, the oval, I should say, in that diagram is was meant to capture V&V and project management and lots of other stuff. So we've simplified that to be just trade studies and the interaction between the different sub-processes that are in that. By the way, you can read all about this. We have a new book out. We call it Real MBSE. And it's model-based systems engineering using LML and Innoslate. There is a lab manual. It is designed as a textbook, and we'd like it to be used as a textbook, and we're hoping that universities and professors will work with that. We do have slides available for the instructors and a sample problem built up in the tool for the students as well. So it's a complete package that we're offering to academia. The part we can provide for free, we do. The books obviously are on Amazon.com, but they're very inexpensive, and you'll find it very reasonable compared to what most people charge for textbooks these days. So as part of that, and in that book, we talk about our processes, and we call our process middle out because it's the one we use most of the time rather than top down or bottom up. And what the heart of that is functional analysis. Our company works on architecture projects primarily for very large scale activities for Department of Defense, particularly, have over the years, many years, worked on some of the biggest architectures in DoD. And so in that, we developed this process to help us do that kind of thing. And the heart of it is functional analysis. We don't start with functional analysis per se. There's a lot of other things we're doing at the beginning of this process, but the critical mass occurs right here with the operational scenarios and the functional behavior diagrams. This is where, by the way, we can do a lot of things that people are asking for in terms of modeling artificial intelligence and how that might behave, because we've been modeling people for years. A lot easier to model artificial intelligence than it is people. So people are much more complex. And so anyway, the nice thing about this is it's repeatable at each level of decomposition. So we can use that. The highly parallel nature of this, though, is enabled by tools. And we've used other tools to do the same process. So this is not, again, it's not a tool-dependent process in that sense, but the type of tool, a real model-based systems engineering tool, like Innoslate, it must be used to do this process well. Otherwise, it becomes a lot more sequential, and it'll take you a lot longer. So talking about MBSE tool, Innoslate, so here's how we think we're advancing the future. First of all, we're cloud native. We started from the cloud development back in 2010 and started on the Google Cloud. So we were on Google Bigtable as our backend cloud. We had hoped people would run to the cloud pretty quickly, but simultaneously with the release of this in 2012, the government came up with something called FedRAMP. Well, FedRAMP threw a real roadblock for cloud developers, because now they were responsible for the entire cloud architecture, and it became extremely expensive to get something certified. It still is, from what I understand, to get something FedRAMPed. So another thing about our tool is, we're working across the whole life cycle. We have the ability to store and share large data sets. With the cloud kind of backing, you can expand to much bigger data sets and work with the things that way. Also built-in collaboration features, that was another big problem we ran into in many of these tools, was working together as a team. You need to work in a common database. And if you're not, then it's really tough to get anything done. I remember one project where we were working with another tool. It took us 18 hours to do a rebuild, merging all the different input files from all the other different developers. I know we've come a long way since that time, but not all the tools have. Also, we don't believe in downloads or plugins. Plugins just are an anathema to us. There's not a feature in the tool we don't think a systems engineer needs. So they're all there and they're all available. Another thing, we are very security conscious. We are 100% developed in the United States. We are available on classified networks and private servers. So it's not just on the cloud, open cloud. There are lots of clouds out there these days, and you'd be surprised what's on them. And then, of course, another thing we've done is use AI in the tool already, particularly natural language processing and actually machine learning. So the way we've used those is for our quality checker for requirements. We also have a traceability assistant to help you with traceability, not just for requirements, but for every kind of traceability you have within all those relationships within the tool. And then Intelligence View. Intelligence View is a set of 68 heuristics provided by some work done by Naval Postgraduate School, Dr. Kristen Gianmarco's, her and her students. And so that's 68 heuristics of what makes a good model. And so we apply NLP to the model and read that information and provide that. So again, this is really, people are asking for cutting edge use of AI in a tool. We're doing it. We've been doing it for years. This is not a new feature within Innoslate. And discrete event Monte Carlo simulators for cost, schedule, and performance. If we're going to optimize cost, schedule, and performance, then we need the simulators to be able to do that and help us do that dynamic side of the modeling. And so that helps us with that. We also have risk charts, both a risk matrix and now a risk burn down chart is coming out in 4.3. So that's coming up very soon. But it's actually been already pushed to the cloud version. So the cloud version, you'll see, has some of the 4.3 features already out there. I think you'll find it's very fast and scalable. And certainly documents as a model is another thing that's unique about our tool. We think documents are still important, okay? I know everybody says model. That's fine, but ultimately I've got to create a legal document that's going to go through that process. And if you don't have some mechanism to easily develop your documentation, you're in trouble. So Innoslate, just as a summary, supports documents view. Again, that's our documentation engine. You can author new documents there. You can ingest documents using the import analyzer and then view them within that view. A subset of that, a specific type, is the requirements view. That brings in our quality checker and other aspects of it, the quality score, things like that. By the way, we've just recently added, of course, baselining, things like that, and we've just recently added an acronym extractor as part of 4.3 input, so you can play with that. It's out available on the cloud today. We also have modeling. So yes, there are 9 different diagram types in SysML. It's not enough. In fact, there's no way to have enough diagram types to show all the different data and all the different configurations you might want it in. We have 24 different diagram types and counting. We are adding more all the time. We have another one planned for 4.3 called an interface control diagram, an ICD. We couldn't find a good standard for that, so we ended up inventing one of our own. Hopefully people will like it. And so again, we have a goal of doing that all the way through. And of course, we also have a charts view. So we have an XY chart and now the risk burn down chart. So again, that's sort of an aspect of modeling, but we call it charting. It's a little different. It deals more with data, ingesting data. We also have a CAD viewer, so we have the ability to view a CAD diagram, break it into its own component assets, and then you'll be able to then you can relate those assets back to the requirements to see if the CAD developer did what they were supposed to do. So this lets you start doing V&V at that level of the mechanical engineering. We are working with other integrations as we speak to do all kinds of amazing things in the software domain and also geospatial. Simulation, discrete event and Monte Carlo are built in. We have the ability in the models to put variations in time or in process, and so those variations can be seen in the discrete event and the Monte Carlo roll-ups. So you're going to find that's very useful. Very often we use the simulation in the early phase of the life cycle to try to understand and predict what we think is going to happen and predict performance. And then in the back end, we're using it to help tie together when we do testing and get results to improve the distributions and things like that that are put in for times and other factors, and then use that to help us be predictive. And now we can create a simulator that can be predictive in the future. And then test center. So we have the ability to capture test expected results, the actual results, status, rolls up the status tracking. Again, all this is related together. And in fact, we recommend you start test center when you start at the top of the V. You should start thinking about how is that going to be operationally tested and evaluated. So that's one of the early documents, at least in DoD, is you're supposed to be creating in milestone A a test and evaluation master plan. This is a place to start that test and evaluation master plan and be working with that capability and with the test plan document we have in our documents view. Of course, you know, that's the technical side of the problem. What about the program management? Well, risk analysis, yes. We do probably in consequences kind of based risk. Timeline analysis, so that's timelines. The nice thing about the timelines, that also links back into the process modeling. And so you can actually do this both statically and dynamically. And then work breakdown structures for costing. That's our cost, showing it as a hierarchy diagram, our cost element. And then of course, those are linked in to the modeling as well and the simulation, and that's how we get the cost schedule and performance together. Okay, so the future of systems engineering is here. So one of the things is the INCOSE president, Gary Rodler at the time, he's just retired, passed on that mantle to Carrie, and Carrie Luna, who was the president-elect, and so she's now the president from Australia. Anyway, but Gary had kind of helped start this whole idea about the future systems engineering initiative and things like that. So this was some of the things he was particularly concerned about. So here's what he thought systems engineering looked like in this environment. First of all, dynamic, non-deterministic, evolutionary. So emergent behavior is common. things like that. Again, we saw that, I think that's been true always because we've had people in the loop. If you're actually doing your modeling with people, you always had this problem. That is not new. That is not a new problem at all. It's still hard, but it's, you know, AI. So AI isn't all what we call, there's hardware, software, wetware, which is the people, and the AIware now. So you have 4 to be thinking about. So that's just very kind of allocation to us. Cybersecurity assurance, it does not need to be integral, not bolt-on. Yes, absolutely. That's why the action diagram works so well. It helps us do that and build it into the process. You have to build in not only quality, you have to build in cybersecurity, information assurance. It's a critical item to be doing as you're going. And of course, new approaches for verification validation. Yes, the current methods we have are very inadequate. The software world has automated testing. We've had automated test equipment in the hardware world for years and years and years. We do automated tests. You know, when you boot up your computer, it's running all kinds of tests. And some of that's in software, some of that's looking at the firmware. So there are various tests that occur. So that actually has been going on for quite some time. Again, that's not overly new, but it's something we got to think about. How do we model that? How do we simulate? How do we work that into the whole process and make it all integrate and flow more smoothly? How do we take the results of that and bring that back up to the developers into the front end of the life cycle and get that working better and don't lose those lessons learned from the V&V process. So again, I said some of these things, the deterministic part, again, LML takes a relationship approach with over 50 relationships with the systems engineers can manage the system by understanding the parts and their relationships. Innoslate gives us both the discrete event and Monte Carlo simulators. Cybersecurity, again, I mentioned the action diagram before. That's important, key part of what we do. And of course, Innoslate is really one of the most cyber secure tools available. It's 100% made in the US. We do care about the classified world and make sure things are available there properly. Also, new approaches that we have direct V&V support within the tool. So that's, again, and the test center helps us do that and documents view. Some of the other ones he talked about was the need for ongoing modeling simulation challenges, ongoing operational changes, and the changes required for a literate workforce. So again, I'd rather than go into that in detail looking at the time, here's kind of our responses to those things. Again, our simulators where we give us the ability to simulate decision processes, particularly that artificial intelligence would make, but also humans. So you can do that behavior modeling is exactly what it's called. And that's what you're looking for. So now you can see that emergent behavior. You can see what the results of running through all the different permutations of it might be. Ongoing operational changes. One of the things we've taken is a digital engineering approach to ConOps, concepts of operations, developing those, and also creating steady flows for stakeholder awareness. And then, of course, changes in the literate workforce. We've spent a lot of time thinking about the language. How do we make the language easier so people can understand it and work with it? Having a collaborative platform like Innoslate works very well. We're in 200 universities around the world. People are finding it very easy to understand and develop and work with. So again, we built that as an educational platform. It's free for educational use. Any .edu can sign up and get it automatically. If you're a foreign country and you have a different .edu your country, then work with us. We'll be glad to set up something special for you too. And so also, how do we improve the technology to make for better systems engineering? So first of all, some of the emerging technology that's available, cloud computing. Well, we've been using it for almost 10 years now. Artificial intelligence, again, NLP's here, machine learning's here. We're using it in our developments, and we want to expand that use in the future. Graph databases are also already here. The problem right now, the reason we're on Google Bigtable, which is basically a graph database, a NoSQL database. We decided to migrate to the SQL Server backend as our primary kind of backend because we found that most of our users were there. And so we need to focus our efforts and energies there. We're going to keep looking for a good portable graph database. One of the ones I like is Neo4j, and we're looking hard at that one. But that will cause us to create two back ends again. And so my developers are going, well, maybe not quite yet. We'll do it soon. And then of course, we're all looking forward to optical computing. We will have to re-architect again for that, I'm sure. But that's okay. That's part of what we're supposed to be doing to keep the tools moving forward in this century. So how can they help us? Again, the cloud computing gives us that collaboration skills, and the systems engineering tools like Innoslate do take advantage of that capability. Artificial intelligence, as I mentioned, is in use. We're using that today. The graph databases give us that greater storage capacity. Again, that we had Google Big Table, but people weren't using it that much, so it's okay. The expansion capabilities that are available on our current provider, which is AWS, are very good too. And we can virtualize servers. There's a lot of growth there. It may not be a full up graph database, but it's pretty doggone good in terms of being able to grow the amount of data you can put into it. Optical computing, of course, we're just waiting for, and can't wait for it. So do we have to wait for years? Well, no, not for most of this. It's already here. Most of these technologies are here today. We're implementing them. We've been implementing them for a while. This is not new to us, and we're going to continue doing more and more of that. Again, LML is an open standard, free for use, not proprietary. Okay, so anybody says it's proprietary, tell them no, it's not proprietary. It's designed to be an 80% solution. That's another thing we recognize, is that any ontology you create is going to have to be modifiable for the specific even project you're working on, but certainly the specific domain. And so feel free to edit it, add to things as you need to. That's why we built a schema extender into Innoslate. We knew that was needed. And so, but most of the time what we find that we're doing is adding labels, because what people really want to do is type the information. So we use labels for typing, and that makes it very easy. Again, it's a simple language, can be extended as you need. Again, we're already using cloud computing, some AI technologies, and it certainly has been designed to scale, and you have to design it for that. Again, do a lot of searching. 4.3 is going to have a significant improvement in the search capability in the back end. We weren't able to get the UI front end search improvements, but we'll probably put that into 4.4. Again, I think you'll find that it's very fast. If you're used to using a lot of tools on the cloud, a lot of them are very slow and hard to use, and particularly some of the government sites are dreadful. And they need a lot of work. Anyway, we've worked hard on that. Our developers think in terms of milliseconds for a function. How many milliseconds is that function going to take? Because I'm going to be doing that repeatedly over and over. If that's going to take me a millisecond, then gosh, I got to make sure that doesn't have to be done 1,000 times. And now all of a sudden it becomes a second, or maybe 10,000 times. All right. So that's a lot of the design part of what's done. And of course, other tools begin to realize these capabilities and are migrating to the cloud. A lot of them are trying to just port their tool to the cloud. That will not be successful. We looked into that at the very beginning. Highly recommend they look at re-architecting their tools for the cloud. That's really what you have to do. So we think the future of systems engineering is here, and we just need to adopt it and move out on it and keep growing it. So we have time for questions. I purposely left some time so we could have some interaction. So Elizabeth, do we have any questions?
Yeah, we've already received a couple of great questions. If you haven't done so, please send your questions to the panel on the right. Dr. Dan will answer as many questions as he can before our time is up. Our first question is, you say LML is simpler than SysML and accessible by everybody. Still, LML contains many more diagrams than SysML. Could you please explain why the first statement?
So first of all, LML only requires 3 diagram types: the action diagram, the asset diagram, so it's the functional and physical diagram, and the spider diagram, which is traceability. Those are the only 3 that are mandatory. The others are just common ways we visualize data and information. And so like a hierarchy chart, things like that. Or if you want to see it in some of the older formats like IDEFs, why not? But yes, we do all the 9 diagrams, but again, you can't get the problem diagrammatically, because if you think about the problem, if I've got 20 classes of information and I'm trying to show information about all those in diagram form, how many diagrams do I need? Is it 20 factorial? That's a lot. That's more than you could ever even envision. And so we got to think about that. So yes, I think it's much simpler.
Great. I just wanted to let everyone know real quick that the handouts are available right now on the handouts panel. If you have any trouble downloading them though, I'll also be sending out an email probably about tomorrow with those attachments. Getting to our next question though, from a psychological point of view, do you think that universally people find it easier to work with models, namely diagrams, than with natural language, spoken or written?
So I'm not a psychologist, so it's a little hard to answer that question. My PhD is in physics, so I'll try to answer the best I can. I do think it's easier to work with diagrams in many ways for some people. Other people are much better with language, and we see that reflected in a lot of places where you try to communicate with people, and some get it visually and others get it verbally. I happen to be a visual learner. That's the way I prefer to see things. So yes, for me, definitely diagrams are easier and models are easier. But the models have to be, I can't create enough models. That's my problem. I can't create enough diagram types to actually show all the data I need. And so I have to do both. I have to have that ability. And as a communicator, I need to be able to communicate in both ways. So the answer is yes, it's an and, not an or.
Thanks, Steve. Our next question is, as a longtime user of MATLAB for DSP algorithm development, does Innoslate support the fidelity of M&S required for detailed algorithm development?
So we are focused in on systems engineering and program management space. MATLAB in particular to me is a design engineering tool for detailed design of things like your algorithms and things like that, level design. That's probably more appropriate in MATLAB. We have just completed a integration with MATLAB. We have not productized that yet, but that's going to be available in the near future. And so we do think that's important. We are trying to integrate with other design engineering tools like MATLAB as well. So the answer is we need both. I wouldn't try to do one without the other, because I ultimately need to be able to take the results of things like MATLAB and be able to bring that up to a higher level so people can see the bigger picture. And so so definitely continue using MATLAB for that algorithm development, but you can then take the results of that and put that into Innoslate and then show that at the broader level.
Thanks, Steve. Our next question is, where can I get the LML book you mentioned?
It's on Amazon.com. Just go to Amazon.com, type in real MBSE, it'll pop right up. Or Essential LML, that's the other book. I mentioned 2, so those are the 2. And if you're doing DoD Architecture Framework, there's a third one, DoD Architecture Framework. So.
Well, we have another question. Similar to the MATLAB question, do you foresee being able to integrate with Python or Julia?
I'm not that familiar with Julia. Python is a programming language, so I mean it's similar. I want to say it's similar to JavaScript, I think. Again, I'm not really that familiar with those particular tools, so so there are other things that we're looking at, and other people who are talking about integrations that would maybe incorporate those kinds of things, and we certainly can look at those other items and see if they're appropriate or integrate with it in the future.
Perfect. Well, that's all the questions that we've received so far. If anyone has any other questions that they think of later, please feel free to contact us. Oh, excuse me, actually another one just came in. Uh, oil and gas is designing systems by numbers in very different environments. Why not with systems engineering?
Systems by numbers. I have no idea what that is. So, um, is that like paint by numbers? I don't know. Since I have no context for the question, it's kind of hard. Oil and gas is using Innoslate, by the way, to do systems engineering work. So as well. So again, I'm just not familiar with the particular technique he's referencing here.
We can reach out to you after the webinar and get a little bit more information on that. I apologize.
Yeah.
And if anyone has any other questions, again, please feel free to reach out to us. We're always available during business hours for phone, email, and we'll go ahead and conclude the webinar with a few announcements. We'd like to thank you again for joining us for today's webinar. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. We would also like to invite you to check out our other resources such as training, books, videos, documentation. You can also join our users group on LinkedIn to get updates on the software, ask other users questions, or see new blogs and webinars. Just search for Innoslate and Systems Engineering Users Group. That concludes today's presentation. Thank you again for your attendance, and we hope to see you again at our next webinar. Please enjoy the rest of your day.